So if I was going to draw like a normal distribution, what would it look like? Bell shape. Bell shape. Careful. Okay. So right in the middle, right. So say like 90 is over here and 10 is over here. Okay. So 90 to 99, is that right?
Mm-hmm.
Yeah. Now when you look at this graphically, how might you explain this? Why the progress might not be equal? Even though it has the same 9% percentile difference between 50 and 59 and 90 and 99.
Well, just looking at it, like the probability of somebody even being in the 90th percentile is very low as compared to being in the 50th percentile.
Right. So we're looking at this as a distribution, and this is a distribution of scores, right? So everybody's score, comes up here. So we have a lot more scores here, right? Mm-hmm. So there's a lot more people right here than right here. So when you do percentiles, what's part of the formula? Below. So if they move here, you have this difference here of how many people are below in that score. So there's going to be a lot more people that he's moving up from rank with, right, in that 9 percentile. Over here, there's a lot fewer people. So when you're changing the formula of people below, it's not going to be as big of a difference because there are fewer people over on the extreme ends of the distribution. Does that make sense? Okay. So again, distribution. And we're using that so we can look at these where an individual falls on a distribution, and there's different ways to do it. So we already talked about percentiles and percentile ranks. We're going to go into z-scores, but before we can even go to z-scores, we have to talk about standard deviation, because standard deviation is part of the formula for a z-score. What is a standard deviation? Yes, very close. Say it one more time.
Like how much, like each one, like each score, like differences. How far away the score is from the norm. So like if the standard deviation is 6, the first one is 6, the next one each falls.
Right. Very close. Who can help refine our answer?
How far a point is from the normal, from like the middle point. From the
but not a point. The average of all points, right? What is the average distance from the mean from all points, right? So you're very close. So you're talking about. Let me change this. So for standard IQ test, the Wechsler, the place, the average IQ is 100 and has a standard deviation of 15. So what does this mean? So it means that the average, say we have, again, it's all these different scores. They're taking the average distance away from the mean, and the average difference for all of these, this standard deviation is 15. But that doesn't really give us much information about the actual individual, right? It just says, like, what is the average distance away from the mean? And it speaks to variability, right? So when we look at, you can have a smaller distribution, standard deviation, or you can have a larger standard deviation. What does it mean when a distribution has a smaller standard deviation?
There's not that much variability.
There's not as much variability. The scores are kind of closely clustered together, right? So it helps explain the distribution some more than just the mean does.
So it means that the value is higher, right?
Right. So it'll be very high, right, with the tails. So they're very, very close together. What about a large distribution? Or a large standard deviation? It says that there's more spread. There's more variability in scores. But it doesn't say anything about individual performance. It's interesting and it brings its own amount of information, but we need it in order to look at z-scores, which gets us closer to how an individual performed. So again, I'm just bringing this graph up again, that you can have the same mean, but but differences in standard deviation. So this standard deviation likely be large or small?
Large.
Large. Spread of the scores. What about this one?
Small.
Small. It's all the same story. You can't get anything smaller than that as far as standard deviation.
So is that the difference by how big it is?
Same one.
Same one.
Okay, who can help her out? Okay, say it again. Who can tell me what a standard deviation is again?
The average of all the distance from each score to the mean.
Right. So it's taking all scores in the distribution, getting the average. It's the average deviation from the mean of the score. Take all the scores into account. So we're not looking at one individual person. We're looking at every life score, right? Every life score. It is interesting. Like I said, it does give us information. So for here, between the standard deviation points, this is how many? 64. I believe it's like 64% of people will fall in one standard deviation from the mean. So if somebody gets here, like in this category, we could say, right, we could expect when they start getting to more of the extremes, it's informative, but still we can't say much about it until we do other calculations.
Can we do an example of it?
Yes, we are going to go to z-scores. And we're going to, right now, we're first going to be learning how to calculate standard deviation. But like I said, we need to find standard deviation to obtain z-scores. And the other nice thing about z-scores is it'll let us compare. It puts everything into a standardized distribution, so it lets us compare scores. So say you took both the ACT and the SAT. They have different scoring systems. They have different standard deviations. Here's like 100. There's, I'm terrible at math. But it's different standard deviation. How do you compare scores, right? By converting them into z-scores, we can see did they perform comparably on both of the tests. And all z-scores have a standard deviation of 0. A mean of 0 and a standard deviation of 1. But first, standard deviation. Here's the formulas. First, we have to calculate the variance, and this is variance here. Standard deviation is just the square root of variance. They just take the square root because it's easier for us to interpret that way. So we find variance first, and that's the formula for variance. Then we take a square root of variance, and that gives us the standard deviation.
What's the variance? How do you explain the variance?
A variance is it's the average deviation around the mean, and the standard deviation is the squared average deviation around the mean. People
What's the variance for? Or just a middle step to get the standard deviation?
That's a great question. It's typically just a middle step. Maybe people who are better at stats than I am will have another reason to obtain variance. Sometimes we'll look more at variance in different equations, like regression equations and some of these other things. But typically, when I see it, people just do this as a step to standard deviation, and they call it variance. Or if they're doing different sorts of formulas for other statistical procedures, they might have, this part of it and part of their equation.
Something else.
But you don't have to know that for this class.
Why is there different Greek letters when there's there?
Like, you'll see it either way. Sometimes you'll see it X bar. Sometimes you'll see it as mu. Mu is typically only done for a population.
Yeah.
Right?
Yeah, France used for sample.
Population. I've seen this used both, but it's typically
Any
for samples.
population over sample. n minus 1, 1 is plus.
Exactly.
Sample, right?
So this formula will take, this is the formula for a population. And later on the slides, there's also the formulas for a sample. A sample, the only difference in the calculation of that formula is n minus 1, because it helps make it an unbiased estimate of the population. You don't have to know why. Just know that it's n minus 1 for a sample and n for...
Second one is for population.
Both of these up here are for population. Both of these that are present. One, the formula on your left is for variance, which we need in order to calculate standard deviation, which is just the square root of variance.
And which one are we going to use? Population or the sample formula? Or depends what
It depends on what you're doing, right?
Are you
So-
going to provide us with the formulas, or we need to memorize them?
Let me think about it.
But most of the time we use
Think about it. For right now, it doesn't matter. You open book.
but right now, but most of the time we use samples, right?
Typically, we use samples, but it's part of what we do as psychologists is to be able to differentiate between the two. So, for example, the homework, I don't know if people have looked at it yet, but you're looking at a class and class grades, right? So, I'm just trying to remember the details of the homework assignment.
I have it here.
You have it here? Okay.
We also have it
So you're helping the professor. Okay. Thank you. All right. So imagine that you're a teaching assistant for a professor who would like you to convert raw test scores into Z-scores and then into letter grades. The professor gives you the following information about the test. The test has 20 items. There are 26 students in the class, and he gives the list of grades and percentiles for which he does a curve. Okay, so 26 students in his class. Is this going to be a population or sample? Population. Why? Because he's interested in his class, right?
Oh, that's right. Okay.
In his class. If he wanted us...
I thought because he was teaching only his class, it was considered a sample.
It depends on what the question is. This isn't worded fantastically to differentiate between sample and population. So on an exam, I will make it very clear, okay, about whether or not it would be a sample or a population.
But in this case, it is sample. So
Population, because he's looking at how are people in his class performing.
Okay.
Okay.
So the population.
No, that's hers.
Oh, sorry. Let me something else here.
I see. So it's sample.
Population. That one is a population. And who, real quickly, can say the difference between a population and a sample? On this example, on the formulas, that's an important distinction to make. It'll make a difference in if you're doing n or n minus 1. So n minus 1 is for a sample. Okay. But what is the difference between a population and a sample?
Population is definitely what you want to study, and a sample would be like a subgroup of the population you want to study.
Exactly. Okay. Most things in psychology are going to be a sample, but not always, but typically, because if I'm going to say I'm interested in how people view unwed mothers, well, I can't survey everybody in the whole world about that. I could do a sample where I might select maybe 20% of the people in the world and ask this sort of questions, but I can't answer that for everybody. But if I said, how do people at the University of Texas Pan Am, what are their viewpoints on unwed mothers? And then if I looked at everybody, it would be a population. But if I took a subset of the students and faculty and staff here, then it would be a sample. Okay.
So like on the class, the homework, wouldn't that be a sample for the only class? Not like the whole university?
It depends on how the question is worded, right? So I want to look at how students in my class performed on students at PMM perform in anybody's class teaching tests and measures. That would each of both of those are population if I look at everybody, right? How would I turn that into samples instead?
The first third class or?
So the first question for population was, I want to know how students in my test and measurements class, how their exam 1 grades are, how they perform, the distribution of that. How would I make that a sample instead? Instead, I'm looking at everybody. I'm looking at everybody in my class.
I want to know
everybody's grades.
How much the females score? That would be population.
That would be a population too. So if I'm saying I want to know how all the females in my class are performing on exam 1, and I look at all females in my class, that would be a population. And if I say I am
10 of them.
Right, I want to know how all the females in my class are doing, but I can't ask all of them, so I'm going to only ask, 10 of them, and use that as an indication of how everybody's doing. That would be a sample of the females from the entire class. So am I looking at everybody, or am I looking at a sample subset of them? All right, standard deviation. So say we have the following scores: 1, 0, 6, and 1. First, find the mean for me. I have the attendance sheet. 2? Everybody come up with 2?
Yes.
Okay, so
Page 20.
okay. So when you're trying to calculate the standard deviation, you're going to make columns like this, okay? X is just the score. So you list down all the scores in your sample population, all the information that you have. And then you take each score and subtract it from the mean. So 1 minus 2, 0 minus 2. And that'll be this column. Because remember, the numerator of the formula for variance is the sum of the score minus mean squared.
What was the middle?
The middle, this is score minus the mean.
Score
Score minus mean. And right now we're doing population. Okay. Score minus mean.
Can I ask you something?
Yes.
Would it change if I did it the other way around?
Yes, you do not want to do it the other way around. You don't want to do mean minus score.
No. Like, I mean, like, the step. Like, for my homework, I did this step first, and then I did that one.
You did this step first?
Yeah, and then when it matters.
It's hard to do that because you have to calculate like score minus mean before you can square it.
Okay.
I mean, sometimes people can just skip the step. Maybe you're really good at math in your head, so you could do like 1 minus 2 is 1, squared is 1, and even if you just bypass this whole column. You can do it if you want, but some people will get confused, so it's easier just to take this part of it first, right? So score minus mean, and then you're going to square each of those. And then you're going to add these together. Okay. Is everybody with me? Everybody
So that's part you're going to add what?
You're adding all of these together. So this, when you see this symbol, it means sum of, right?
Yes.
You do score minus mean for every single score. You square every single score, and you add the squared values together. And that's how you're going to get the numerator. Have I lost anybody?
You add the square.
So that's going to be 22?
22, right. So that's then we have the numerator for variance. The denominator is n because it's a population. So in this example, we have 4 scores. So it's going to be 4. So variance is 22 divided by 4, which is 5.5. You get the standard deviation, you take the square root of that. It's going to be 2.35.
Square root of 5.5, right?
The square root of 5.5. So everybody with me?
No.
Okay. So here's the formula we have for standard deviation. Okay? The formula for standard deviation, and we start with variance first, right? Because standard deviation is just the square root of variance. And which of these formulas are variance? If you ever look, the first one. Variance, standard deviation. So we have to make these calculations. It's easy to do the denominator, right? So for this example, we have 4 scores. So that's all we have, right? So the denominator is going to be 4.
Which is n.
Which is n. If this was a sample, the denominator is n minus 1. So that would be 3. But this example that we're doing right now is a population. We're going to stick with 4. So we already have the denominator. That was the easiest thing to get. The more difficult part of this formula is to get the numerator. And what does this part of it mean?
That's the score.
The score. So this score minus mean. So that's what it comes to this chart here. So we're listing all the scores we have. So if you had 75 scores, you have 75 rows. Okay? You have to subtract the mean from every single individual score in your sample or population. Okay? Whether it's 4, you have 75. You have to score minus the mean. That's this column. So we're getting this part here, right? But then we have to square them before we can add all of them together. So our first step is to get this part for every single score. And then we have to square it for every single score. Okay? And then the whole numerator then is going to be the sum of this column here, the sum of squares. Okay? Yes?
For the homework, do we have to use that formula? Can we use like a different formula?
It's up to you. It's up to you. If you were, I talked to somebody else today that said it was easier to get another formula from another class or another book. As long as you're coming up with the same one, it's fine. Okay. I'm kind of on the fence about this book. I don't love this book, but I didn't really have a lot of choices. I think it gets complicated. Yeah. I would go with that. Go with what works as long as you know that you're doing it correctly. You can go with something else. Okay? So the last step, so we got the sum. We've got a sum of squares there, which is 22. So now we can finish out our calculation of variance. The first step. So our numerator is 22. We found the denominator 4, so we divide 22 by 4, and it's 5.5.